So I'm recording this on a very, very stormy August day in Wellington. And August, generally the beginning of term 3, means that we're into the run up really to the exams. So from here on, I'm going to be doing all of the calculus exams from 2015 to 2025. I've already done the 225 ones and I think a couple of the other ones. But let's start with differentiation. It's the one that most students do. So this is 2015. I'm going to be using the exam that's on the NCEA website and the most common exam calculator, the Casio FX98. And I'll also be using the formula sheet wherever possible to solve these equations. So just a quick note, I'm going to be using Leibniz notation. So I'm going to be using kind of this notation rather than this notation, which means that I'm going to probably be using this notation rather than the F prime notation of the Laplacian notation, the Leibniz notation. I'm also going to be using U substitution for the chain rule, product rule, and quotient rule. I just prefer it that way. So if I have a function within a function, I'm going to be using U. If I have sort of functions within functions within functions, I'm going to be using V and W, and hopefully that's all I'm going to need to be using. Okay, with that, let's do it to it. So for these, this is going to be the first time I'm seeing them. I've had a quick scan through the paper. I think one of the questions, the one right at the end, I might need to hit pause and kind of do some scribbling to work it out, because I don't think you want to see me scribbling around and cursing. So question 1, we're told to differentiate y equals 6x brackets 5x. So I could think of a couple of ways of doing this, but we're going to use the chain rule. And the inner function, I'm going to set u be equal to 5x. So y is going to be equal to 6 tan of u, and u equals 5x as I did before. So dy is going to be, what's it going to be? There's going to be 6 secant squared, isn't it, of u, and du over, that's a u, not a y, du dx is going to be 5. So dy dx is going to be 5, which is this one here, times this one here. And of course, u is just a dummy variable that we put in there. So the final answer is going to be 30 secant squared of 5x, and that's done. All right, next one. We're told to find the gradient of this function, y equals brackets 4x minus 3x squared, all cubed at the point 1, 1. We'll take this when x equals 1. So you must use calculus. Okay. So for this, I guess we could take this one here and kind of expand this bracket out and get a big long polynomial, but kind of it's going to be a waste of time really. We're going to use the chain rule again, so I'm going to let u be equal to 4x minus 3x squared, so that way y is going to be equal to u cubed. So du dx is going to be 4 minus 6x, and y with respect to u is going to be 3u squared. So our final answer is going to be dy dx is therefore going to be 4 minus 6x times 4x minus 3x squared. Looks really nasty, but it's not really. So that's going to work. So let's just substitute x equals 1 into this. So we've got 4 minus 6 times 1 is 6 times 3. 4 times 1 minus 3 times 1 squared is 3, all squared. So 4 minus 6 is minus 2 times 3 times 4 minus 3 is 1. 1 squared is 1, so it's going to be pretty easy. So minus 2 times 3, so it's going to be minus 6. So the gradient, I prefer to write it this way, is going to be minus 6 over 1. I always write it as a fraction because remember it's rise over run. All right, on to part C. So for this one here, we're told that find the values of x for which this function here, f of x, is increasing. So if we see increasing here, we know we're going to need to differentiate this. It's in Laplace notation, so I'll keep it in Laplace notation, I guess. We're going to need to find that, and we're going to need to find where it is strictly greater than 0. That's our condition. So how are we going to do it? We're going to divide and conquer. So if I have f of x, here is 8x minus 3 plus, and I'm going to rewrite this as 2x plus 1 to the power of negative 1. Notice that these two are the same. And we're going to differentiate each of these terms separately. So f prime of x, when we differentiate the first one, we're going to get 8. When we differentiate the second constant, we're going to get 0. Okay, so the second one, I'm going to use u substitution again. I'm going to use the chain rule. So I'm going to say let u be equal to x plus 1. So therefore du dx equals 1, which is good. So that means we're going to differentiate 2u to the power of negative 1 with respect to x. And when we do that, we get negative 2u to the power of negative 2 times 1 here, du dx, which is going to be 8 plus negative 2, so I guess this plus is redundant, u to the power of negative 2, which I'm going to rewrite again in this form here because I think I can see what's going to come along. When we have an inequality here, having negative indices always gets kind of messy. So I'm going to rewrite that in terms of x minus 2 over x plus 1 square. Okay, so now we've differentiated it. Now we need to find this condition is greater than 0. So 8 minus 2 over x plus 1 square greater than 0. Let's bring this term over by adding it to both sides, and it helps us get rid of those pesky negative signs. So 8 must be greater than over x plus 1 square. And now let's multiply both sides by the denominator here. So 8x plus 1 square must be greater than 2 over 1, which is going to be good. Let's divide both sides by 8. My pen doesn't die on me. Divide both sides by 8, so x plus 1 square. And for some reason my pen is just messing up on me. It must be greater than a quarter. Okay, does this help us much at all? Yeah, I guess it does. So we're going to use the square root of g is going to be equal to g squared is going to be equal to the absolute value of g, which is plus minus g, just so we're kind of here. Okay, So therefore, x plus 1 must be greater than 1, the square root of a quarter. Now, square root of a quarter is not an eighth, it's a half. So just kind of recap, half times a half is a quarter. So this is going to be a half, but it's going to be plus minus a half. So how are we going to do this? So let's sort of split it. So we've got x plus 1 is greater than positive a half. I'm going to take 1 away from both sides. So x must be greater than, so half minus 1 is minus a half. Okay, so that's one of them. And the other one is going to be x plus 1 greater than negative a half. So x must be greater than half. Yes. Yes. X must be greater than, no, it's not. It's going to be greater than 3 over 2, isn't it? Because half minus 1 is minus 3 over 2. Yes. Oh, where does that leave us? No, I've messed it up, haven't I? I've got this the wrong way around. So this is going to be, it's going to be less than 3 over 2. Sorry, my bad. Oh, what does that mean for us? It means that x must be less than 3 over 2 and greater than a half. Yes. Than negative 3 over 2. And x must be greater than negative 1 half. So where does this put us? Are we going to write that in 1? Must be less than 3 over 2. So negative 3 over 2. And must also be greater than negative 1 over 2. If we want to write that in one line, I think that's right. Yes. Good question, though. I guess if we were to write that on the number line, we would have a gap here down to negative infinity and negative 3 over 2. And then it's going to be from here negative a half to positive infinity if we wanted to do that on the number line. So the open circles means is strictly less than or strictly greater than. All right, the next one says, what are the values of x, the tangent of x, where this graph here, this beast here, is parallel to the x-axis. So what does that mean? So parallel to the x-axis has a gradient of 0 because it just goes from left to right. So in other words, we're going to find f prime of x and we're going to set it to 0 and then solve for x. Okay. So let's have a look at the original function that we've got here. And we have a couple of things to note. We have a sort of a quotient, a rational function here. We have a polynomial at the top and we have a polynomial at the bottom. The one at the bottom, the denominator, is factorized. I'm going to get rid of that factorizing. It's for now, so we don't have to sort of worry about the product rule inside the quotient rule or anything like that. So let's just expand that out. So this bit at the bottom here is going to be x squared minus 5x. It's just, if it's simple like that, you might as well keep it in that nice polynomial form. So f of x is going to be x plus 4 over x squared minus 5x. And I'm going to use the quotient rule. And the reason I'm going to use the quotient rule, I try to avoid the quotient rule, but there is going to be a kind of a hack here that we can use because it's equal to 0. So remember the quotient rule is v du dx minus u dv v squared. And we use that when it's in the form, the thing that we're trying to evaluate is in the form u over v. So let's take u here and differentiate it. So du dx is just going to be 1, which is pretty good for us. And dv with respect to x is going to be 2x minus 5. All right, let's collect up these terms and put it in a form there that we can use. My pen catches up with me. V x squared minus 5x times du dx, so that's times 1, I guess, if we really want to do that, minus, and now it's u, which is x plus 4 times 2x minus 5 all over x squared minus 5x all square, and we set that equal to 0, and that equals 0 is going to help us a lot because we're going to not care from here on about what's in the denominator. Because if we multiply both sides by this, we're just going to get x squared minus 5x times 1. And then we're going to need to expand out these brackets, I guess. So x plus 4, 2x squared plus 8x plus 20 equals 0. Let's put a little gap there so we don't get them mixed up. And now let's simplify this a bit. So it's going to be negative x squared, taking care of those, minus 8x, taking care of those, plus 20 equals 0. And now we can really use the calculator to find what the values of x are. So let's use our calculator. Again, this is calculus, it's not really algebra. So polynomial solver, this is degree 2, negative 1x squared, negative 8 and 20, just to be lazy. So x is 2 and minus 10. So x is 2 and x equals minus 10. Let's do a bit of a sanity check. If we put 2 and or negative 10 into the denominator here, does it equal 0? No, it doesn't. So that must be our final answer. So on to the excellence questions. We're told that salt harvested at the Grasmere Salt Works, I think it's in Marlborough, falls from a conveyor belt. The slant of the cone forms an angle of 30 degrees with the horizontal as shown there, and the conveyor belt delivers salt at a rate of 2 meters cubed per minute. So 2 meters cubed, and time is in minutes. So time is in minutes and volume is in meters cubed. And we're told that the angle it makes is 30 degrees. Find the rate at which the slant height is increasing when the radius of the cone is 10 meters. And we are given these formulae here for the things that we want. So slant height isn't in the volume here, but it is here, and they call it L, so we're going to call it L. I'm going to use that sort of curly L. So knowing that the angle there is 30 degrees, we can sort of look at it. So if we look at the pile kind of like that, and we know that this angle is 30 degrees, and we draw a line straight down, that's going to be H, that's going to be R, and that's going to be L there. So from that we can work out L in terms of R and in terms of H, because we need it for this one here. And we also need to find L in terms of R, because we're told in the initial condition that the cone is 10 meters. So what are we actually trying to find, and what have we got? Well, we've got the theta angle is 30 degrees. So they give it to you in degrees. So in the exam, you're going to need to be careful that you change your settings to degrees and from radians. We're told that the radius is 10 meters when we're testing it. We're told also that the change in the volume with respect to time is 2 meters cubed. So change in volume with respect to time is 2 meters cubed per minute. All right, so let's work out L in terms of H and R. Really, it's R in terms of L and H in terms of L, to be fair. So H is the opposite side, L is the hypotenuse side, so we can use sine. So sine of 30 degrees is going to be the height divided by the slant height. So that tells us that H is going to be the slant height times sine of 30 degrees. Now sine of 30 degrees though is half. So H is always going to be half of L. Okay. So therefore, if that uses sine, then the other one's going to use cosine. R is going to be L times cosine of 30 degrees. And I think in the formula sheet they give you, that's going to be L times square root of 3 over 2. I think they give you cosine 30 degrees as square root 3 over 2. But it is square root 3 over 2. So first off, we're going to need to change the initial condition so that it's not when R equals 10, it's when L equals a number. So if R equals square root 3 over 2L and R is 10, then L must be equal to 10 divided by square root 3, which is going to be 20 over square root 3. So we're going to evaluate that when L is 20 over square root of 3. So let's convert this formula here for volume. It's currently in terms of R and H, and let's convert it so that it's in terms of L. So the volume as a function of the slant height is going to be pi over 3 times R squared. So it's going to be square root 3 over 2L squared times H, and H is given as half L. So let's expand things out, and it's really just a matter of algebra now. So it's going to be pi over 3 times 3L squared over 4 times L over 2. And the reason I do that is so that we can multiply the top and the bottom. So it's going to be 3 pi L cubed over 3 times 4 times 2 is 24. So that's going to be pi L cubed over 8. And I'm going to rewrite that so we have the constants out the front. Pi is a constant. Okay. So now we're going to tie all of these equations together. So change in volume with respect to time is going to be change in volume with respect to L times change in L with respect to time. And that's what we're going to be what we're trying to look for. we know that this is 2. So let's put like a little note under there. That's going to be 2. We don't know what this is, but we can work it out here. So if v as a function of L is pi over 8 of L cubed, therefore v prime of L is going to be 3 pi over 8. 3 pi over 8. Yeah, 3 pi over 8 L squared times change in L over change in time. And I guess this really should be dv there rather than in that format there. But we know that that's going to be 2. And we know that L is going to be 20 over square root of 3. So this is 3 pi. Sorry, my computer's glitching out today. Times 20 over square root 3 squared, because that's going to be L, times the change in L over the change in time. Okay. So 2 equals that. So let's get rid of these brackets here. And my pen is glitching out of me again. Sorry. So it's going to be 3 pi over 8 times 400 over 3 times dl dt. Okay, so 2 is going to be equal to, some nasty number. So it's going to be 1200 pi over 24, and they're going to cancel. So 1200 over 24 is 50. Yep, 50. So it's going to be 50 pi. So then we want to multiply that by the thing we're trying to solve for. So that tells us that change of L with respect to time, when we bring this 50 pi over there, must be equal to 2 over 50 pi, which is 1 over 25 pi, and that's going to be meters per minute. So 1 over 25 pi, I don't know what that's going to be, 20 pi, a really, really, really small number. I'd rather keep it as 1 over 25 pi. So on to question 2. So this question wants us to differentiate this function, and it's to the 5th power. So 2 things we've got to do. We've got to rewrite this in our polynomial form, and we've got to find what we want to use as u, because the u is going to be doing all of the work. It's going to be chain rule. It's going to solve this. So if u equals x minus 3x squared, then du with respect to x is going to be 1 minus 6x. And if we wanted to rewrite f of u, that's going to be u to the power of 1/5. So what is f prime of u? Well, it's going to be 1/5 of u to the power of minus 4 over 5. And the chain rule says we have to multiply that by this thing here. So f prime of x is going to be 1/5 of u, but u is just a dummy variable, so u is up here, x minus 3x squared is 1 minus 6x, and that's got to be to the power of 4 over 5, doesn't it? And that's think probably about as simplified as you'd want to get. It just wants you to differentiate. It doesn't want you to make it all pretty. Maybe I should rewrite that a little bit because it kind of looks a bit funny. So 1/5 x minus 3x squared to minus 4/5, and then maybe times 1 just to show that that's owned by that. Right, next question. Find the gradient of the normal to this graph y equals x minus 16 over x at the point where x equals 4. So the normal, remember, is the line that is perpendicular to the tangent. So if the curve here is like that, then maybe that's a really, really bad rendering. If the curve is here, the normal will be at right angles to that. And the way we work it out is that the gradient times the gradient of the normal is perpendicular. When we multiply them together, we get -1. Okay, so if y equals x minus 16 over x, we need to either use the quotient rule, which seems a bit of overkill for this, or we can rewrite it x minus 16x to the -1. And now we can use the polynomial rule. So dy dx over of x is 1, and then minus 1 times minus 16 is positive 16x, and then we lose 1. So we've got dy dx. So now we need to evaluate that where x equals 4. So I'm going to evaluate that where x equals 4. And for that, we've got 1 plus 16 times 4 to the power of -2. And I'm going to grab out my calculator. So 1 plus 4 to the power of -2. And that gives us 2. So in other words, the gradient of this one here is 2, which means that the gradient of the perpendicular to that is going to be -1 over 2. Because 2 times gradient perpendicular is -1. Therefore, when we rearrange that, it's going to be -1 over 2. So to these questions where they show you the graph and they want you to know about this graph, and it's a piecewise graph, so it sort of goes up here and then it has a turning point here. It looks like it has a saddle point here, and then it goes up like that. So it's concave down, concave up. There's a jump here, a piecewise jump at x equals -1, and then there is an asymptote here, and then there is another piecewise kind of leap here. Alright, so find the values of x which meet the following conditions. F of x is not defined. Well, it's going to be x equals 1. So it's defined here, it just jumps. It's defined here, it just jumps, but here there is an asymptote. So where is it not differentiable? Well, it's not differentiable here, it's not differentiable here, and it's not differentiable here. If it jumps, you can't differentiate it at that point. So when x equals, what is that, -1, x equals 1, and x equals 2. So whereas f double prime of x greater than 0, that means it's concave up, or as we used to call it, convex. So it's going to be convex between here and here, because it's kind of, the bowl kind of points upwards. So that's when x is greater than -1 to x equals, I guess this goes on for 1. So on that kind of -1. So for that, we'll just do some cleaning here. So it's later. So what's the value when f equals x equals -1? Well, here is -1. It's not going to be 2 because it kind of goes there and then it sort of stops. There is a circle there which is empty, but then it's here. So it's kind of a strange graph. It kind of goes up there and then it goes up here like Pac-Man and it goes back down again and keeps going up. But this is where it is. If we put in this formula here, x equals -1, we would get 3. So what is the, you can see that, so it's the limit where x goes to 2 of this function. So this, we have to say it does not exist. So our answer is does not exist, and then you put an exclamation mark because it is kind of a crazy question. Okay, so now we have a really, really classic calculus problem. So a street light is 5 meters high above the ground, which is flat. So let's start labeling this. This is 5 meters, and whatever is 1.5 meters. So let's kind of get that 1.5 meters. Walking away from the point, so he's going over 2 meters per second. What is the length of his shadow changing when the boy is 8 meters away from the point? So this is going to be 8 meters directly under the light. Use calculus to solve this. Okay. So first thing we've got to do some next statements. So I'm going to say let this distance from here to it's on the x-axis, so I'm going to call that x. And then the length of the shadow here, I'm going to call that s. Purely because it's the shadow. This triangle here that I've just done, it's similar to this main triangle here. And this distance here, if this is 1.5 meters, this distance here must be 3.5 meters. Okay, so we can exploit similar triangles in this case. And we know that the change in x with respect to time is just get a few equations in the handwriting, and because these are similar triangles, this big one here, x plus s, yes. So this side here over x plus s must be equal, must have the same ratio as this triangle here, 3.5. So we have an equation here with x and s. So let's take the algebra and do equations. So 5x plus s equals 3.5x. And let's get x as a function, s as a function of x in this case. So we want this s. So let's cross multiply. So as we've got 5x equals 3.5x plus s. And that means it's going to be equal to 3.5. 3.5x, so 1.5x is going to be equal to 3.5s, which means that we subtract, when we divide both sides by 3.5, s is going to be equal to 3.5x, and that's going to be, okay, this should be able to work this out pretty easy, but 1.5 divided by 3.5, I think that's 3 over 7. So s is equal to 3 over 7x. So now we can find x prime of time. It's going to be change of respect to x times change of x with respect to t. And we're going to get the initial condition, and that's when x equals 8. Okay, so that's what we're looking for. So the difference with respect to the change in the shadow with respect to x, we work that out already as 7, and the change of x with respect to t, we work that as 2. So I guess this is irrelevant. So it's just going meters per second, and it was. So this last question 2, is that what a container is constructed in the shape of a pyramid, square base. So that tells us a lot here. It's square base, and the height of the pyramid is the same as the length. Okay, well, this tells us a few things. If they give us the volume here, so it tells us the volume with respect to h is going to be h squared over 3 times h, which is h cubed over 3. The surface area, we'll call that A, is going to be h squared. So if this is h, this must also be h. Okay, but things get a bit funny. They cut 20 centimeters off the top, so they lob this bit off, and they start pouring water in at the rate of 3,000 cubic centimeters per minute. So what have we got? We've got here change in the volume with respect to time is 3,000, and the unit is centimeters, and it is in minutes. Okay, so it's inverted. So they cut it off, then they take it upside down, and then they say that they want you to find the rate at which the surface area, so it's going to be this one here that we're going to need to solve for, is increasing. The depth of water is 15 centimeters. So it's they want, what do they want? They want change in on the rate at which the surface area. So they want change in A with respect to T. Okay, we have to do a couple of things first off, because we have to use both of these, because the thing which is changing is the volume. The volume is changing. We don't know what the change in H is, and we're told to find it when the depth is 15 centimeters, not when H is 15 centimeters. So for the depth here, I'm going to sort of draw a line here from the apex to the height of the water, whatever the water is. And I'm just going to call that X. So what is X in terms of H? Well, H is going to be X plus 20, which is good because now I can have the volume and the area in terms of X, and the condition that they give us is in terms of X. So I'm just going to move down a bit and then we'll finish it. Right, so the volume is for the full pyramid here is h cubed over 3. But remember, we cut this bit off, this little bit off, and that's when h is 20. So it's going to be minus 20 cubed over 3. And this must be a similar, if this is perpendicular to the height, this must be a similar pyramid. Okay, so that means that the volume as a function of h is h cubed over 3 minus 8,000, yeah, because 2 cubed is 8. It's going to be that. But we want to find the volume as a function of the depth x. And we know that h is x plus 20. So x plus 20 cubed over 3 minus 8,000 over 3. And if we differentiate that, we find the difference in v with respect to x. So change in v with respect to x. And we're going to use the chain rule for this one. I think I'm going to make u be equal to x plus 20. Actually, we could have done it with h, couldn't we? So du dx is one. We could have just reworded this as h, just looking at it. So the h is u over 3 minus some constant, and that constant is going to disappear. So that's going to be u squared, isn't it? And this is going to disappear, which is good because that's going to be x plus 20, times 1, of course. That's going to be x plus 20 squared. Okay. Now we're into it. Fantastic. Okay. That is going to be h squared, which is going to be good because that's going to be x plus 20 squared, which is exactly what we had up here. Fantastic. The change in a with respect to x is going to be, what is it, 2x plus 20 times 1. This is going to be 2x plus 40. Fantastic. And we have enough to go now, I think. All right. So the change in volume with respect to time is the change in the volume with respect to x times the change in x over the change in time. We know this is 3,000. The change in volume with respect to x, well, we don't necessarily know, but we know we're evaluating this where x equals 15. So this one here is going to be 15 plus 20 squared. Remember, this is x there, times whatever this thing here is, and we don't know what that is, and we need to find that. So using a bit of algebra, bringing this across, change in x over change in time is going to be 3,000 divided by 35 squared. 1,000 divided by 35 squared. I always put them in brackets in these KCA calculators. It's a nasty number. 120 over 49. That's a nice one. 120 over 49. And that's going to be in meters per minute. Okay, so now we have change of x over change in time. Now we need to find change in area with respect to time. So change in area with respect to time is going to be the change of the area with respect to x times the change in x with respect to t, which is what we just found. And what's this going to be? Well, we're going to evaluate this where x equals 15 again. So the change in area with respect to time is going to be, what was change in a over x? 2x plus 40 times 120 over 49, evaluated where x equals 15. So 2 times 15 is 30. 30 plus 40 is 70 over 1 times 120 over 149. And we have enough for a final answer. So I'm going to multiply that by 70, about 7 what's that as a decimal? Ugh, nasty. 171.43 decimal places. And what's the unit? It's going to be, is it meters? Was it meters? It was centimeters, wasn't it? Centimeters squared per minute. We're done. Question 3 already. For what values of x does the tangent to the graph of the function f of x equals 5 natural log 2x minus 3 have a gradient of 4? So in other words, they want you to differentiate that and set it equal to 4 and solve for x. Okay, so if f of x is 5 natural log 2x minus 3, I'm going to use the chain rule. So u is going to be 2x minus 3. So du dx is going to be 2. What's going on there with my pen? And f dash of x is going to be 5 times the natural log of u, which is 5 times 1 over u. And now we've got enough. So we've got 5 times 1 over u times 2, which is 10 over u. And u, remember, is a phony dummy variable that we just put there to make our life easier. So that's when we differentiate it, and we set that equal to 4 and solve for x. So 10 2x minus 3, and we set that equal to 4. So let's just cross multiply. 10 is going to be equal to 4 2x minus 3, which is going to be 8x minus 28. 4 8's 28. What am I doing? It's 12. 8x minus 12 equals 10. So 8x minus 12 equals 10. I'm going to add 12 to both sides. So 8 equals, x must be 22 over 8, which is a number, 2.75. So there. So part B. So f of x is this thing here, and we want to find where the derivative equals 0. So kind of the same as the other one, but a bit more spicy. All right, well, if f of x is that, I'm going to write it in a slightly different way, so I don't need to use the quotient rule. Quotient rule can get kind of gruesome. We've got that, and we want to differentiate it. Okay, so I'm going to let u be equal to x, and I'm going to let v be equal to e to the negative 3x. So du dx is going to be 1. dv with respect to x is going to be minus 3x. Differentiated is minus 3 e to the minus 3x. So dy dx to f of x is going to be equal to minus 3 e to the negative 3x plus e to the negative 3. And there's a common term there, so let's take that out. E to the negative x plus 1, and we want to set that equal to 0. And we see a problem here because this cannot equal 0 no matter what x equals. So let's divide both sides by that. So if we divide both sides by that negative 3x, though, we get negative 3x plus 1 equals 0. And now it's going to be a lot easier to solve. So negative 3x equals negative 1. X equals 1 over 3. So we get to the parametric question. So a curve is defined parametrically by the equations x equals 3 cos of t and y is sine of 3t Find the gradient of the normal to the curve at the point where t equals pi over 4. So that's a sort of reminder that we're now back in radian space. Use calculus to solve any derivatives. Okay, so using the parametric formulas that are given to us, what are we trying to find? We're trying to find this, and this is going to give us the gradient of the tangent, and the gradient of the normal to that curve is going to be that m1 equals -1 business. So dy dx is going to be dy over dt, and if y is sine of 3t, then I'm going to set u be equal to 3t. So dy with respect to u of sine of u is going to be, it's going to be cos of u, because of u, and that's going to be multiplied by du, which is going to be 3. So dy dt is going to be 3 times cos of 3t. So 3 cos 3t, and dx with respect to t. So we're going to differentiate this one now with respect to t. And I'm going to, what am I going to do there? It's just going to be minus 3 sine of t, isn't it? Yes. But remember, it doesn't want of x. That's pretty easy to do. We just find the reciprocal, 1 over that. So dy dx is going to equal 3 cos 3t times 1 over -3 sine of t, which is going to be -3 cos of 3t over 3 sine of t. They're going to cancel. And do we have enough now to find what that is? Yes, we do. So we're going to evaluate that where t equal, what was that number? Pi over 4. And it's going to be negative cos 3 pi over 4. I don't know what that is off the top of my head. Over sine of pi over 4. Grab your calculator and get your engines rolling. So negative. So this way, negative cos 3 pi divided by 4. Below this though, actually. Divided by 4. Divided by sine of pi over 4 is that 1. Oh, okay, 1. So that gradient there is 1. Therefore, the gradient of the normal is equal to -1. If you wanted to write it like that, -1 over 1, if you wanted to be really, really pedantic. Okay, the last couple of questions. The equation of the motion of a particle is given by the differential equation. Second derivative here is equal to -k squared x, where x is the displacement. So this, a physics student should see this as a simple harmonic motion. where x is the displacement from the origin at time t, and k is a positive constant. So what can we take from this? Well, they tell us that the equation here, a solution. So a solution is if we double differentiated this thing here, we would get this thing here. What else do they tell us? They tell us that k is a positive constant. So k is a constant greater than 0, and it's a member of the real numbers. And they tell us that a and b here are also real numbers and are constant. And here's the table that they give you in the exam. Okay, so what do we need to do? Well, we need to double differentiate this thing, differentiate it twice with respect to t. So we need to differentiate with respect to t twice and see if we can get it to go into this thing here. Okay, let's have a look at it first. So what I'm going to do, I'm going to split it into these two bits. So the a cosine of kt and the b sine of kt. So for both of them, I guess the inner function is this kt bit, and du dx is going to be k. So whatever we differentiate here, we're going to need to put k out the front. And these a and b are constants, so we can just bring them out the front when we differentiate them. So when we differentiate this, we've got a, and then we differentiate whatever this thing is, cost of kt. Oh my goodness. A times differentiate cos of kt. Well, when we differentiate cos, we get negative sine. So this is going to be negative a, and then we have to bring this k out the front as well, and that's going to be sine of kt. And then we need to differentiate this thing here, and when we differentiate sine, we get cos, and this is when we differentiate it, we've got b sine of kt. So that's going to be bk, and then cosine of kt. Fantastic. So let's differentiate that twice. This is going to be positive. So therefore dx dt is going to be, I guess we could say, negative ak sine of kt plus bk cosine of. Now we need to differentiate these again. So let's differentiate this thing separately from this thing. And the good thing is that negative ak and bk are both, they're all constants, so we can just bring them out the front. So when we differentiate with respect to t, we get minus ak dt of sine k of t, and the kt is the inner function again. So when we differentiate sine, we get cosine of x. So it's going to be minus a k square, because the k comes out the front, cosine of kt. And then when we differentiate this one here, it's going to be bk, differentiate with respect to t, cos of kt. Well, we've already done that one, so it's going to be bk square. And then when we differentiate cos, we get minus 1 minus sine, and it's going to be minus sine of kt. So when we differentiate this, differentiate it twice with respect to t again, we get minus ak cosine of kt. Now let's go back to the original. What have we got? We've got this thing here, and we've also got this statement here. So can we, oops, there should be a square there. can we differentiate this or factorize it? Well, we can. There is a common factor here, and it's minus k squared. So minus k squared, and then this is going to be a cosine of kt plus, because there's a minus k squared, plus b sine of kt. Lo and behold, we see that that is indeed equal to x. So the second derivative of time with respect to second derivative of x with respect to time. Sorry about that. We just had a guest come around. Where were we? Okay, so when we do that, we can see that this is x. So this tells us that this second derivative here is minus k squared times x, which is what we had right at the beginning here. So yes, it is one of the solutions for that differential equation. We're now told that the particle was initially moving at the origin. So it was initially moving at the origin with a velocity of 2k, which tells us a lot, which tells us that x, when time was 0, was 0, and it tells us that the velocity at time 0 was 2k. We can use that now to find a and b in the solution. Remember that a and b are constants, so they can be greater than, equal to, or less than 0, and k is also a constant greater than 0. So we know this. Let's have a look to see what we have here. We know that when t equals 0, x equals 0 as well. So if we let t be equal to 0 and x be equal to 0, we're going to have this. 0 equals a cosine of k times 0 is 0, plus b sine of 0. Okay, cosine of 0 is 1. Sine of 0, however, is 0. So this term disappears. So 0 equals a times 1. So therefore a must equal 0. That's a done. Now we're told the initial value was 2k. Well, we solved for the velocity. It was, which one was this one here? Minus ak sine plus bk cosine. So the velocity, I guess we can say the velocity at time t is minus, what did I say it was? Minus ak sine of kt plus bk cosine of kt. Okay, so we know that the velocity at time 0 must therefore be equal to minus ak. We'll ignore the fact that we know that a is 0. You'll see why in a second. Sine of 0 plus bk cosine of 0. And we know that that equals 2k. That's the initial velocity. We know that that sine of 0 is 0. So this disappears again. So we know that this equals 1. So bk must equal 2k. Again, it's pretty trivial. We divide both sides by k. They go to 1. B equals 2. So a equals 0 and b equals 2. It's a really nice question. This last one caused all sorts of problems in the exam. A lot of students really didn't like it. I know when I saw it just now, I thought, oh, this looks a lot like a another question that I had way back when I was an undergraduate at university doing calculus. So it's a nasty one. It is the excellence question though. So our corridor is 2 meters wide here. So here, 2 meters to 2 meters here, and it turns 90 degrees into another corridor, and presumably this is not 2 meters wide. So what is the minimum width W of the second corridor that a ladder of length 5 meters can be carried horizontally around the corner? Presumably you want to do two things there. You don't want to break the ladder, and it has to be a straight line, and it's going to be a triangle. So let's fill in what's missing here. That's a right angle. That's a right angle. This side and this side here add up to 5. So I'm going to call this one L. And I think the trick to this one is going to be knowing your trig identities and minimizing variables. So we could call this one L1 and this one L2 and add them together, but I'm not going to do that. I'm just going to call this from here to here. I'm going to call this L, and I'm going to call this 5 minus L, I think. Just minimize these straight away. So A is the same, W is the same. Okay, how are we going to do this one? Let's solve it for L. So L, so this is going to be, if this is our theta angle here, this is the adjacent side. So cosine of A is going to be equal to the adjacent, which is 2 over L. Which is good because now we can swap those. So L must be equal to 2 over cosine, and therefore, therefore if we W here, we can do W in terms of L now. Yes, we can do that. So let's work out what W is in terms of L. So this side here is going to be 5 minus L, and that's the hypotenuse. So W over 5 minus L. So cosine sine of A must be equal to that. So it follows, therefore, if we multiply this cross multiply, so 5 minus L times sine of A must be equal to W here. Yes, that's going to work. But then we want these in terms of, do we want it in terms of L or A? Where's the minimum width? Let's do it in A. So L in terms of A is this thing here. So therefore, 5 minus 2 over sine A equals W. Is that going to work? Yes, that's going to work. Let's get rid of this bracket then. So 5 sine of A, I'm going to use brackets from here on in, minus 2 sine W. And if you remember your trig identities, sine of theta over cosine of theta is tan of theta. So 5, because I don't want to be using the quotient rule for this. Sine of 5 sine A minus tan of 2 tan of A equals W. Okay, so now we have W in terms of A. So let's rewrite that and differentiate it. Minus 2 tan of A. Okay, so then we want to differentiate this, don't we? And there's So you want to differentiate W with respect to A, because once we've got A, the W will kind of pop out, won't it? Yeah, well, because here's our kind of function that's going to be doing all the work. So when we differentiate 5 sine of A, we get 5 cosine of A. And when we differentiate tan of A, we get secant squared of secant squared of A. And we want to set that equal to 0. Now it's going to be nasty when we come to do that, because the Casio calculators don't like secant squared. They don't really like that, but knowing that secant of theta is 1 over cosine of theta, so therefore secant squared of theta is 1 over cosine squared of theta. Let's bring this one across and collect up all of these cosines. That'll work, yeah. So 5 cosine of A is equal to 2 secant squared of A, which is equal to 2 over cosine. So 5 cosine of A. And then we bring these across. So 5 cosine cubed. Ooh, that's going to be a bit nasty. Of A equals 2. So therefore 5 cosine cubed of A minus 2 equals 0. Or we could just keep it there like that. And then we would use our calculator. So for this one here, now we can work this out. I'm going to set that equal to 2 or leave it there. If we do this one and do it on the calculator, you need to use solver. For this one here, you could either use solver or you could use graph mode. Now, there was a bit of a problem here. I kind of had to pause the video because the calculator completely died on me when I tried to put this in. So you've got to put it in on some of the older calculators as 5 times cosine of A times cosine of A times cosine of A minus 2 equals 0. Or if graphing, find the root, which I'll show you on this calculator now. This is quite an old emulator, so it's probably why. So I put it in, so 5 times cosine x times cosine x times cosine x minus 2, and I come to draw it. It gives this weird, funky looking graph, and I find the root. It finds this root first, it finds this root second. We can't have negative values, so this must be the one that we're looking for, 0.4246189, and this one here is going to be too far along. It must be this one. This is more than 2 pi. So using A is 0.74246 radians. Remember, this is in radian mode. We should be able to find, using the original equation, what W was. So A we've got equals 246 radians. I don't know what that is in degrees. And then we're going to put that into the equation up here. So 5 sine minus 2 tan. So W is 5 sine A minus 2 tan of A. So 5 sine of 0.74246 minus 2 tan of 0.74 is going to be, let's have a look. So 5 times sine of 0.7424 minus 2 tan 0.7. equals 1.545 meters, and that's the final answer. Now, this one here, you could go down a rabbit hole. I think this is, I sort of simplified this as much as I could at the beginning to make it easier. Get rid of variables as quickly as you can and know your trig functions. Other than that, pretty good exam though. Okay, exam.
Wait.
1, 2.
There's two now.